So, um, first things first. We've got a bit of a disaster piece here. Um, the lab that is supposed to be going with today's lecture. Um, Somehow, I have not realized this, or I guess it didn't connect. I'm fully aware that Flash is no longer supported. However, it just didn't connect in my mind that this simulation we use actually runs on Flash. All of the PhET simulations, they've got a variety of different things that they run off of. The newest generation of them all runs in HTML5, so it runs right in the browser. Right before that, they were using Flash, so it would similarly run in the browser, and then before that, they were using Java. But the simulation that we need to use is unfortunately right in the middle generation where it only has a Flash version. And it doesn't run in web browsers anymore, not since the 31st. And to make it even more upsetting is that they actually did an alright job of it, and if you don't have the most recent version of Flash, being the one that doesn't work anymore, it won't play the Flash simulation. So it's a combination of a mess. Somebody brought it to my attention yesterday, and I've been trying to find solutions. And if you saw my excited face just a couple minutes ago, it's because I finally got something that would actually work with it. So I think what I'm going to do here, it is no longer going to be a required assignment by any means, because realistically, the process that I had to go to get this thing to work was a nightmare. Not a fun time. But what I am going to do is I am going to upload, essentially, I have downloaded the Flash file at this point. I'm going to talk about a program that I use to actually make this thing run as well. I will have both of those linked on Canvas. The assignment is now going to be an optional one, no longer going to be required, but there is going to be a little bit of extra credit associated with it if you choose to go through it. So no points against you if you don't want to do it, if you don't want to fight with the downloads and the programs and everything else, because I can't guarantee that it's going to work on everyone's computer. I can try to help you troubleshoot with these things, but I have just kind of on a lucky break, I feel like, actually gotten this thing to work myself. So that's the update for that one. I'll have that changed after we get out of the lecture from today. I'll send out a short little thing about that as well. It's a mess. It's what it is. I'll have it, for the download, I'll have it linked on, I'll upload it to Canvas, so there's no confusion about what things to download or anything else like that. Yeah, having a romp of a time with this one. But once we get through all that stuff, we'll get this all taken care of. All the good stuff like that. Again, if you choose to do it, it is going to be optional at this point, though, because I'm not going to ask anyone to actually go through with these things and download a bunch of files on their computer or anything else like that. So, with all that in mind, though, let's go ahead and get into the material from today. And this evidence that I've been lying to you, this is not even the first time, right? Realistically, we talked about this a lot last time, about how essentially from the very beginning, we started from a very simple picture, and I tried to kind of ready you for this. The fact that I was going to lie to you, you know, to kind of explain, hey, we're taking a simplified view of what's going on, right? We said no air resistance, we said no friction, we said gravity's a constant. We said block uniform mass. We don't worry about the size of the block or anything else like that. And we kind of knew that was a lie, right? Come on, like there's no such thing as a frictionless surface. There's no such thing as no air resistance. Even in space, there are particles. There are hydrogen and helium atoms floating around that, technically speaking, in space, there is still air resistance. It's really, really tiny, but it's technically there. But it's been all right, because for the most part, we have been focused on the concepts, and we said it's too complicated to look at some of those things, right? Think about last time when we looked at the pulley that actually has mass and friction, right? Suddenly, what was once an easy problem was suddenly a little bit more complicated, because we had a third equation showing up, and we had new terms floating in, and right? Some stuff like that. But that's the name of the game, because technically speaking, if we wanted to dive into it all the way, all of classical physics is a lie, right? I'm sorry to burst the bubble on that one, but everything that we have learned so far, technically speaking, is just a bit inaccurate for what is actually happening. And to be honest, we don't know what the actual accurate picture is quite yet. when we're talking about like quantum mechanics and general relativity, all of those things actually play into what we would be seeing here, but the part that they play is so incredibly small that why bother with it? Really, it's been kind of a running joke in our department here because the university gets after us to say, you know, are you updating the pedagogy? Are you including the most recent material into your introductory courses, stuff like that? And we have to politely tell them, hey, classical physics hasn't seen any updates for the last 150 years. We're not getting anything new in this material. It's pretty well set in stone at this point. It's not going anywhere. But why do we still use it then? Right? Because it's still accurate for the most part. If we use classical physics, if we use orbital motion, if we use a lot of these things, we're going to get 99.9999% of the way there without needing to introduce uncertainty and general relativity and the speed of light and things like that, right? So why would we bother with a much more complicated equation when realistically we could stick with the simpler stuff, get there faster, and still be most of the way right? So, I am going to pick apart at some of these lies. We are going to further complicate the picture just a little bit, but we're not going to go super crazy. We're still in the realm of classical physics. So, what is the theme of today's lie? Well, it's gravity. What we have known to be the force of gravity, mg, not actually accurate. In reality, gravity is a force acting between any two masses in the universe. That means right now, you are pulling with a gravitational force on Sirius some 200 light years away? I don't even know how far away that star is. Every object in the universe is pulling on you with a gravitational force right now. You are pulling on every object in the universe with a gravitational force right now. And it is not mg. In fact, it is this more complicated equation, capital G, m1, m2 over r squared. So what is in this equation? Well, of course, it's our two objects, the mass of each object. Gravity is a force acting on the mass of objects. So if I have two objects, m1 and m2, what I would do is I would take the mass of m1, I would take the mass of m2, I would take the distance from the center of mass of m1 to the center of mass of m2, call it r, square that value, multiply it by this gravitational constant, capital G, and now you have the force between those two objects. So it is our first of what we call an inverse square force. Electromagnetism is the other inverse square force. There are two other forces, though, two other fundamental forces that we know of. Does anybody know what those two forces are? Remember the names or anything else? They're not very creative names. Electromagnetism sounds pretty cool. Gravity, it's like, all right, yeah, gravity, I get that. There's some cool stuff with that. What about those other two forces, though? Does anybody know what they are? The strong and the weak force. Yeah, we were running out of inspiration when we named those two. But that's exactly what they are. Strong force and the weak force. They act on a nuclear scale, which means they don't act actually outside of the atom. They are so incredibly weak outside of the atom that we didn't notice them for most of human history. It wasn't until pretty recently that we actually discovered those two forces. Because they go as something like 1 over r to the 12th, and I think they've got a 1 over r to the 6th kind of term in there. They're really weird. They don't have such simple equations anymore, actually. They've got some weird stuff going on with them. But they don't act outside of an atom. Gravity and electromagnetic force both do, but we're going to focus on gravity for now. Electromagnetics for next semester. But the inverse square force, that's basically saying, hey, it is inverse distance squared. So it doesn't decrease at a linear rate. It decreases as 1 over r squared. That is, the farther away the two objects are, the weaker the gravitational force. That's why, despite the fact that the sun is really, really big, it doesn't pull you in. Right? There's a little bit of a difference between those two things. That's why, despite the fact that the sun is much more massive, it doesn't pull the moon away from Earth. The moon is closer to the Earth, so that r squared term right there means that the moon is going to feel a stronger gravitational force to Earth than it is to the sun. It's going to stay spinning around the Earth. Along those lines as well, gravity is always an attractive force. always an attractive force, right? When we plug in these quantities right here, we know that the direction of the force is always pointing from one object to the other object. Gravity always wants everything to be as close together as possible. That is not the same for all forces. So I just want to kind of bring that up. We're not going to focus on those other things right now, but gravity is always an attractive force. So I want to try something real fast. Take this brand new equation that we've got right here, g m1 m2 over r squared, and let's try this out. Let's imagine here, what is the ratio of the sun's gravitational force on the moon to the Earth's gravitational force on the moon? And you'll notice here that we don't actually have a distance included in this table for the moon to the sun. This value right here, the asterisk, has something going on down from here. However, I don't see it in the sky right now, but most nights, I think the moon is somewhere nearby Earth. I would believe that it would probably continue to do that. That makes sense to me. So how's about for this one, we say that the distance of the moon from the sun, because it's orbiting around Earth on average, it's the same as how far the Earth is from the sun. Let's just assume that value. That'll make that a little bit easier, especially because it's a few orders of magnitude difference. That slight variation would be anyways. So I'm going to say take the next 4 or 5 minutes. Try this one out. Let's see if we can get some good numbers, and then we'll come back together and see what you got. All right, so let's start taking a look here. So first things first, of course, we draw a good picture, right? Because that's what we always do in all of these problems. And let's do it like this. So we'll start with the sun. And how do we know it's the sun? For one, it's a giant orange-yellow ball. But for two, of course, as we have always seen the sun depicted, it's got these really cool shades. And that's how you know. Look up in the sky. It's too bright to actually see the sunglasses, but they're there, I promise. You see all the depictions of it, of course. Now, this thing has a pretty intense mass here, right? If we look at this value here, we've got a mass of 1.99 times 10 to the 30th kilograms. Still about 3 orders of magnitude larger than the largest planet in the solar system. So the sun is pretty significant, right? It is no small thing. But let's go ahead and write down some of these values. And what I'm going to do is I'm going to try and label all of these. Whoops. So I'm going to call this MS, mass of the sun, 1.99 times 10 to the 30th. Kilograms, of course. And then we will have boring old Earth drawn out here. And then the moon drawn out here. So let's label some of these values here. What I'm going to do with these things is I'm going to say, all right, distance from the center of mass of one to the center of mass of the other. So let's start from the sun right here all the way out to the center of mass of the moon. That straight line right there is what I will call R sub S. Radius from the sun. I'm going to do the exact same thing with the Earth. Call it R of E, radius from the Earth out to the moon. And then, of course, these other quantities that we've got, we're going to have the mass of the moon, should we need it, is going to be 7.36 times 10 to the 22nd. Mass of the Earth, a little bit larger than that, right? Something more like 5.98 times 10 to the 24th. And all of these are in kilograms. So the last thing that we would need for all of these things would be, what are these two quantities? We said go ahead and just take, essentially, because the moon is constantly spinning around the Earth, and they're pretty close together realistically. Actually, if you look at the scale of these things, the distance that the moon changes from the sun is really not that significant as it orbits around the Earth. So I feel pretty comfortable using that value. I will call this value R of E. Oh no. Come on here. There we go. R of E is something like 3.84 times 10 to the 8th. R of S is more along the line of 1.55 times 10 to the 11th. 1.50, if we want to follow the table, 10 to the 11th meters. Okay, with all of that stuff in mind, now we are asked to find what is the ratio between these two forces. That is to say, what is the force from the sun relative to the force from Earth? Force of sun relative to force of Earth. I'm going to write in both of my equations at this point. So I would say G, I'm looking at the force between the sun and the moon. So it's MS divided by the distance between the two, R sub S squared. Divided by the exact same force, but now with Earth. So that is mass of the Earth, mass of the moon, divided by the distance between the Earth and the moon, squared. Now I'm looking at these two, and I could say, all right, top and bottom, they both have a G. Top and bottom both have an M. Cancel out both of those. Turns out the mass of the moon doesn't actually get a say in this matter. Now, I'm going to take everything that's on the denominator, move it over to the other side. So this is going to become mass of the sun, radius of Earth, squared, divided by mass of Earth, radius of sun, radius from sun, I should say, squared. Plug all of that stuff in, and what we should find here. Okay, and I know what I'm goofing up here. I know what I'm thinking about in the wrong way. This number is correct. But my explanation was a little bit strange. My explanation that I had for this thing was actually incorrect. And why is it incorrect? This is basically saying to us that the force from the sun is larger than the force from the Earth. So why is the moon not orbiting around the sun? Do we have any guesses here? Any explanations for why this might be? Yeah, the moon is orbiting the sun. Right? That's really what I should have been going with here. The moon is technically orbiting around the sun. It's just orbiting also Earth at the same time, right? If we actually go through the spiral of this thing, and let me pull up, I've got let me find this thing real quick, and I can show you exactly what I'm talking about here. Talking about all of these simulations and everything else, there is a newer one that technically works in browser, but it doesn't have the same features as last time, but it does have this stuff. Let's let this thing load. The model of this thing, right? Let's go ahead and add in the moon. Watch what happens. And I'll even have the paths with it as well. The moon does orbit the sun. It's just at the exact same time, it's orbiting around the Earth. Both of these things are making a path around the sun, though. So I don't think it's that surprising to see that both of these are having some sort of impact on what the moon is doing. So I apologize. My description of that was wrong. I was thinking about that the wrong way. Sometimes that'll happen. But that's exactly what's going on with this thing. The sun's force is a bit larger. It's just the moon is going around both at the same time. So, does that all make sense? Does the answer seem reasonable? Are we feeling all right with all of that stuff? Apologies for the confusion, but we got there in the end. Even I still make all sorts of mistakes in my problems sometimes, and I know this isn't the first time, so that's probably not a surprise at this point. But I can show that again, sure. It's probably not a huge surprise that I make mistakes at this point, but you know, that's why we don't expect you to get every single one of these things. That's why we've got the grading scale as it is and everything else like that, because sometimes the explanation's just wrong. Sometimes we think about it the wrong way, and that's all right. That'll happen. It's a cool kind of shape. You're welcome to try these out as well. These don't have the same problem that some of the other ones did. You should be able to run these on just about any computer you've got. If it's got internet access, it should be able to run these things. Why is the sun not moving? Because for the most part, the force from the Earth and the moon are pretty insignificant for actually how much the sun moves. And this is a model. This is what we would call like a fixed sun model. Technically speaking, the sun does wiggle a little bit as well, because of course it does feel a gravitational force from the Earth and moon. However, remember that there's like a 4 or 5 order of magnitude difference between those masses. And with that 4 or 5 order of magnitude difference means that the acceleration that the sun feels is going to be very, very, very small as compared to the acceleration of the Earth. And actually going back to something like this other simulation that I was showing, that's kind of what's happening here. The Earth is like what's going on the outside. The sun is like what's going on in the middle. The sun does technically orbit around, but it's just such a tiny amount that it doesn't really matter. So, that's what we got for this one. 2.18 is what Canvas is looking for, by the way, as well. That wasn't screwed up. I just suddenly had a weird doubt about my numbers. I looked at something, I thought about it a strange way. 2.18 is the number that we're going for here. So, speaking of the pull from Earth, right? We have been using mg this entire time, and I have not said that anything is wrong about that. And, well, it's still pretty accurate, honestly. All of the stuff that we have learned so far is not useless. We're still going to use mg, we're still going to use mgh. It's still got its place. The difference here is that it only really works on the surface of Earth. And I know I've talked about this before, but now we've got a little bit more context to that discussion. If we take that force equation, and if we said, okay, the force from Earth, I would take the mass of Earth and the mass of myself, divided by the radius of center of mass of me to the center of mass of the Earth, which is just about the Earth's radius, right? Roughly speaking, I'm standing on the surface of Earth, and the 70 centimeters? Sounds like a little bit more than that. Up from the surface to where my center of mass would be is really pretty negligible compared to the full radius of the Earth. So we plug in the radius of the Earth, and we divide by m on either side, and we would see that the free fall acceleration is right around 9.8 meters per second squared. The exact same value that we've been using the entire time. And you can go up a pretty high distance before that starts to change. It's not until you're getting it, up further into the atmosphere that this starts to change a little bit to where we would want to, kind of worry about that a little bit more. But for the most part, it's not something that we really need to consider. But it is kind of a cool thing because there's a lot of things that actually go into that value. For one, the fact that the Earth is actually rotating means that the actual free fall acceleration we feel is a little bit less than what we would from gravity, because technically there's a centrifugal force kind of acting on us as we're rotating around. But even more than that, it turns out that the force of gravity from Earth is not actually a constant value over all of Earth. So this is a really cool graphic right here. Let me ask you a quick question. Who is the #1 climate research agency in the world? What's the biggest research agency for the climate? Does anybody know? Have a guess? It's NASA. NASA's got all the equipment for it, right? Like, the local weather channel doesn't have, satellites up in the air watching what's going on with Earth. NASA actually has all of the equipment there, and they're an extremely important part of understanding how the climate's changing. So this in particular was taken from a particular mission called GRACE, and there were a couple different varieties of GRACE, but GRACE was a really, really crazy thing. What goes on, it was a series of satellites, and those series of satellites were essentially measuring how much gravitational pull was coming from the Earth at different locations around the Earth. And this has a number of different reasons why. For one, the Earth doesn't actually have a uniform density, right? Different parts of the Earth have different densities. For two, you might see as mass moves one way or the other, whether it be the tides or ice or rock or whatever else you might be seeing there, that shift of mass is also going to cause a shift in the gravity felt in that particular region. And this was actually a really cool project and very important for understanding what the ice sheets are doing, because a lot of those values that you see about how the ice sheets melt and then come back and everything else, those are images from NASA. And a lot of the time they were using a program like GRACE to actually study that, because that ice had a mass to it, and that mass was causing an ever so slight shift in how much gravity was felt in those regions. So it's a really cool thing, and they can really see the impacts of, how the mass of the Earth is shifting around the surface. It's a really fascinating kind of thing. Now, the value that it actually shifts is small. It's incredibly small. It's an extremely minute difference, you know, a 0.0001% change of gravity, depending on these different spots. So it's not really anything that we have to consider about, but at the same time, we might remember again that, hey, even this is technically, well, this one's pretty accurate, but using our mg, using some of these values that we have is not completely accurate. There's some differences here that we're just not considering in the same way. But if you want to read more about that, I've got a link down here to that mission from their official page. You can read a little bit more about what they're doing with all that good stuff. But that's how we actually come up with the 9.8, right? That value that I've been feeding you this entire time, this is where we get it from. So with that in mind, let's try something here. Let's imagine planet Z has a diameter of 10,000 kilometers. The free fall acceleration, their little g, is measured to be 8 meters per second squared on the surface. I want you to find two things. First, what is the mass of Z? And then let's imagine that somebody goes 10,000 kilometers up from the surface of the planet. What is the free fall acceleration all the way up there? So take the next 4 or 5 minutes, work on this one, and then we'll come back together and see what you got. All right, so let's go ahead and start taking a look here. And let's go ahead and draw this thing out. So, I don't know. I assume it's some sort of alien planet or something. That sounds fun to me. So let's go ahead and label it like this. Planet Z. It's a big Z etched into the side. And I am going to keep saying Z and Z together because, well, I mean, I was born and raised in the Midwest, so it's always been Z to me, but I realize that some people call it Z instead, but whatever mess it is anyways, we'll just kind of deal with this as is. So what we're imagining here, though, is that we are standing on the surface of this, and we have, I don't know, a block. We drop it, we measure what the free fall acceleration is, because that worked incredibly well when we did it in a lab, right? We found values all over the place for that one. There's a much easier way, but we have to have some special equipment that makes it a little bit better. So if you're looking for a little bit of context on that one, we would have done that had we been in person, but we would have had a much more accurate way to really just kind of show like, wow, that was terrible. Timing those things is nearly impossible. But I do promise that it does actually work. But that's kind of beyond the point at this point. We're focusing on what's going on right here. So we would say this radius from the center to where we are at right now, I'm going to say you are not any meaningful percentage of 5,000 kilometers tall. So the height of the person, whatever mass it is on the surface here, really doesn't matter that much. But we are talking about 10,000 kilometer diameter. I say U, diameter? No, radius. 5,000 kilometer radius, or 5 million meters. So let's talk about those values. We would say at this point right here on the surface, our acceleration, free fall acceleration, 8 meters per second squared. Radius away from the center of mass, 5 million meters. Gravitational constant capital G is 6.67 times 10 to the negative 11th. And then all we really need to do here is we need to go through the same steps that we just saw for how do we calculate little g. We would say, all right, well, with all of this stuff, if we are in free fall, if gravity is the only thing acting on us, then our net force, ma, is equal to capital G, mass of the planet, mass of the person, mass that, divided by r squared. I don't need these little m's, right? Whatever acceleration we find, free fall acceleration, should apply to every single object, regardless of mass. We're looking for capital M here, so all I'm going to do is I'm going to move some stuff over. AR squared divided by G is equal to capital M. Plug all of that stuff in, and at the end of the day, what we should find for that quantity right there is something like 2.998 10 to the 24th kilograms. And there's our mass. So the second part of this is, let's imagine we are now 10,000 meters above the planet, off the surface. So we're floating up here. I'm going to call this value right here. For one, we know that this height right here, let's go ahead and label this. Stuff is not particularly well drawn to scale, but that's all right. This value right here, this is our 10,000 kilometers above the surface. So let's label this new R. I will call this R of F, R of floating. So with that in mind, now what we're going to do is we're going to say, all right, find the acceleration now. Same deal. Acceleration is equal to G capital M over RF squared. Plug all of those numbers in, and what we should find is something like 0.889 meters per second squared. All right. And so now I did want to bring up, somebody made a comment of how did we actually measure the mass of the sun? And I'm not entirely sure, to be honest. I think it's a fantastic question. I don't have a great answer for it, though. But what I could imagine is that I imagine one of the best ways to go about doing this is essentially to look at the orbits of the planets around it. See, when we're looking at it like something like this, a free fall acceleration, well, this works for any radius that I would want to plug in. So if I could observe what the orbits of each planet were surrounding the sun, I could find essentially, I could relate their motion around the sun with, okay, well, it has to depend on the mass of the sun. And if we compare all of those values, they should come into some good agreement. And then the closer we follow those distances, the more accurate we can be with those distances, the better picture we have of what that mass should actually be. I would guess that's at least how we got started with it. How we go beyond that, I imagine that there is a lot of different precise ways they look into this thing, but beyond that, I'm not entirely sure what they might be. So, but I could imagine this would be a very good way to look at different masses of different objects to see what's going on with them. Radius for the final part, that is just our 5 million meters that we had from before, combined with our brand new 10,000 above that surface. So that radius final would be something like 15 million meters. So, let's go ahead and keep diving into some stuff then. Now, of course, talking about forces, particularly gravity. The gravitational force is no longer just mg. So when we're finding the work that gravity would do, it's not just going to be mgh anymore. But is gravity still a conservative force? That's a good question. Let's imagine something. Let's imagine you're going for a long walk. You've got a really flat, straight piece of road, say 2 miles long. You walk that entire way. I think we could all agree that if all of our old stuff is still true, the gravitational force we would feel in magnitude would still be mg the entire time. But let's say you go on a really long walk. Let's say it's like 30 miles. Does the direction of gravity stay the same the entire time? Yes or no? What do we think? And bonus, if you can include a little bit of explanation, a little bit of reasoning why you think it's yes or no. You can think about this for a minute. Wouldn't it always be pointing towards the center of mass of the Earth? I would agree. So it's kind of like a reverse trick question here, because I would have taken either answer. It's always pointing in the radial direction. Yes. At the same time, because as we're moving, where the radial direction points is technically shifting, at least in like our old Cartesian coordinates, x, y, and z. You know, you could either look at it as it is always pointing towards the center, or that it's constantly changing because it has to be pointing towards the center. Either description I would agree with. But the fact of the matter is that regardless, as we're walking across the surface of the Earth, the force of gravity didn't change. It was mg the entire time. And since we're going tangentially around this big sphere, there's no work to be done. There's no change in our potential energy. So I bring that up because I want to extrapolate that description. What if we take that description to something like the International Space Station? The International Space Station maintains an altitude around the Earth, constantly spinning. Sure, it's not quite mg anymore because g is no longer 9.8 at that altitude. But even if we were to use our force of gravity that we have just learned, as long as they maintain the same distance away from the Earth, the force should be the same the entire time. It shouldn't change. And if they're constantly rotating in the same circle the entire time, their gravitational potential energy shouldn't change either. And arguably, no work was done. And that means that gravity is a conservative force. Despite the fact that it is changing with distance, it can still be a conservative force. That's not a big deal. Because what we're going to find one day is we're going to do the exact same thing with electromagnetism. But we'll get back to that one later. What I'm trying to say for now is that the force of gravity only depends on the distance away. It is not actually a path-dependent force. Unlike friction. Right? It doesn't matter if I pull the planet away and then bring it back close or anything else like that. That has no bearing on what force it's going to feel at this moment in time, depending on where it is at. So it's a conservative force, and if it's a conservative force, then there is a potential energy associated with that conservative force. This is our new expression for the gravitational potential energy. How did we arrive at this equation? Of course, the exact same way that we had arrived at this equation. We take an integral. Potential energy is the negative of the work. The work done would have been the force dotted dr. Since none of these other quantities change, 1 over r squared is the only thing that actually matters there. Well, I'm left with this. Negative g m1 m2 over r. Just r, not r squared. So, now the question becomes, what do we call 0? Because realistically, every single time we've been talking about gravitational potential energy like this, we've always said that the ground is 0, or most of the time we have said that the ground is 0, and that's been all right. That's not been a big deal. But realistically speaking here, we've got a standard that we hold to for a lot of these things, and that is that out at the edge of the universe is where gravitational potential goes to 0. And any closer than the very edge of the universe, it is some negative quantity. So this is how we typically are going to address what goes on with the gravitational potential energy. Of course, the change of that potential energy gives us some sort of kinetic energy, or rather a kinetic energy can turn into a change of potential, and that's all fine. But the standard is that the edge of the universe is going to be where we call 0. Everything else closer than that, everything, is just going to be some negative quantity. And if we remember, if we take this description the other way around, if we remember that force is a derivative of the work, then this makes sense again. Because, of course, the lower the potential energy, that means that objects want to go there. Objects always want to go towards where the lowest energy is. That's why most of the time, electrons aren't just orbiting atoms in like the 100th shell. They're down as far down as they can possibly go. They like to be as low of energy as possible. So objects that are experiencing gravity like to be as close together as possible. So I want to take this idea. And let's introduce one new concept for this as well. The escape speed, or the escape velocity, is essentially how fast you have to be. If I am launching off of a planet, how fast do we have to be so that we can actually get away from the planet, so that gravity isn't going to suck us back in? And the way that we measure this is that we say by the time we reach the edge of the universe, that's when our kinetic energy goes to 0, or just about 0. If we run out of kinetic energy anytime before that, then gravity is going to pull us all the way back in. We might be away for millions of years, but it'll still eventually pull us back in. So the speed, the escape speed, is the minimum speed that it takes so that we can get away from the planet and we're never coming back. So of course, with any time varying force, conservation of energy was typically the easiest way to approach many of those. Same deal here. Use what we just saw with that gravitational potential energy, use what you already know about kinetic energy, and use those conserved quantities to come up with what is the minimum speed to get away from the planet. And then plug numbers in that would be relative to Earth, and we'll find out what it would need to be. What does NASA need to launch our rockets at to make sure they actually get away? Give it the next, say, 4 or 5 minutes, and then we'll take a look together. All right, so let's start taking a look here. So, of course, we start with a very good picture, and what's a better picture than let's go ahead and draw the planet. Fun thing is, I talked about there's technically a little bit of air resistance in space, but it's so incredibly negligible that for the most part, we generally don't worry about it. And that means that when you're talking about spacefaring ships, the shape doesn't actually matter. So there's our spaceship. There's our planet. Let's say the planet has a radius, capital R, and a mass, capital M. Capital M, this is capital R. Our spaceship, mass little m, and what we're going to do here is we say that this thing starts with some initial velocity, v0. And what we want to do is we want to launch this thing out so fast that it never, ever, ever comes back. So a straight line all the way out to the edge of the universe, all the way out here. It still exists, right? Still doing its own thing. But now, let's go ahead and do this as like a dotted line here. This is the path that we have traveled all the way out to the edge of the universe. And we hope that we've still got a little bit of juice left over. We're still moving just a little bit. But now we're at some distance away. How far away? Ideally, the radius of us now is equal to infinity. So, energy conservation. Name of the game. What type of energy do I start with? What do we think? What do we expect to see on this left side, the initial column? I wouldn't say all gravitational potential, some gravitational potential, but of course we have to start by launching the rocket. There has to be some kinetic energy with it as well. So let me write it out like this. I would say that we start with our launch velocity minus, because it's always a minus now for gravitational potential, the largest it could possibly be is 0. But this minus right here is going to be capital G M over capital R. Now, we go out to the edge of the universe, and let's go ahead and be complete with this thing. Let's go ahead and write out 1/2 mv final squared minus g m over, and I'll call this R, well, let's just do R final. So even if we're not at the edge of the universe, this would still apply, right? This still relates our energy when we start to our energy when we end. But our conditions are the minimum speed so that we actually get out there all the way. So what is any number divided by infinity, first of all? 0. Yeah, anything divided by infinity is 0. I would even argue 1 divided by 1,000,000, that's practically 0. I'm not going to worry about a number that large. So this term certainly goes away. And since we're talking about the minimum speed, that is to say we just barely make it to the edge of the universe with nothing left over, that is to say that our V final approaches 0. The mass isn't going anywhere, but if V final approaches 0, if it's very nearly 0, then I can cancel that out as well. And here's what we're left with. And this is why our kinetic energy does change, because gravity is a constant force pulling us backwards. If our velocity was going straight out, gravity pulls us backwards the entire time. So there is some acceleration that we would be feeling from this. Now, for each of these things, I'll go ahead and cross this out in a slightly darker red. I don't need the mass of the rocket, mostly because it wasn't given, but it shows up in both M's right there. Cross it out. We're looking for this V0. So it's going to become, first, 1/2 V0 squared is equal to g m over r, right? Because the whole right side of this thing turned out to be 0. Multiply both sides by 2, take a square root of each side. Here is a final expression for what the escape speed must be. If we plug in common values for Earth, g still 6.67 times 10 to the negative 11th, but we plug in the mass of Earth, we plug in the radius of Earth, and what we find when we do all of those values, that we actually end up at a speed of about 11,000 meters per second, or let me just write it out like this, 11.2 kilometers per second. So, I know a lot of people keep loving to bring up Elon Musk and SpaceX and all those things, or even if we're just talking about NASA. Does anyone launch a rocket at that speed? It's not even just that it would be risky. Think about what goes on with, for one, yes, it would be pretty risky. I take that back. It would be pretty risky to try and even do something like this. But rockets aren't launched by slingshots. There's no crazy belt or spring systems launching them off. They're powered by rockets. They start from rest, and somehow they still get out into the upper atmosphere. Now, there's a couple things they do to help with that. For one, they discard mass as they go up, right? Think about all the booster rockets, and those booster rockets will fall off once their fuel is out, because realistically, all they're doing at that point is weighing us down. So less mass means less energy to actually get all the way up there. But in addition to that, realistically, this much speed, do you remember what drag looked like? It had a v squared thing going on there. The faster you go, the more air resistance you're going to feel. The more energy air resistance is going to be taken away from your rocket. So when we're talking about it like that, it makes a lot more sense to try and go at a little bit of a slower speed the entire time. Energy conservation is not broken, though. Energy conservation is still in effect. It's just, where is our energy starting? When NASA launches a rocket, when SpaceX launches a rocket, where does the energy start? What other form of energy do we have? Any guesses? Chemical, exactly. It's chemical energy. All of the fuel yet to be burned has a bunch of chemical energy. As the fuel is burned, it converts all of that into heat and mechanical energy, and it propels the rocket with a thrust. That's exactly it. And by doing that, by reducing the kinetic energy that we've got, or rather by reducing the speed, we don't have to fight with air resistance quite as much. So, not a very practical way to launch a rocket, but it does give us an idea of what it takes to actually get away from a planet when we're trying to launch off of it. Because that's how we are going to be defining gravitational potential energy. When we're talking about large-scale potential energy like this, where mg is no longer doing the job for the gravitational force, it's always going to be that we say the edge of the universe is 0, whereas everything else beyond that, so if I draw it out like this, let's imagine we have reached now the edge of the universe. And if we have reached now the edge of the universe, if we're already out here on the side, this is where gravitational potential is 0. That is our starting point. And then everything beyond this is where gravitational potential is less than 0. It's always going to be a negative value. The closer you are to a planet, the more negative it becomes. You can never leave the gravitational pull of a body of mass. That is true. Yes. But looking at it like this is essentially saying that we have enough kinetic energy that no matter how far out we go, we are never going to get pulled back. Because it's not a constant force. The farther away that we get, because it's going as a 1 over r, the farther away we get, the smaller the force is pulling us back, the less energy it takes to keep going a little bit farther. So as long as we have enough velocity to keep going, the amount that it's going to be taking from us diminishes, goes down to some sort of limit, and we'll still have a kinetic energy where we continue going on forever. But that's kind of a question of, like, what's going on with the universe? Is the universe ever going to collapse back down? Is gravity going to be enough, or are all of the particles in the world at such an escape speed that they will never collapse back down into a singularity again? And I don't have an answer for that one. I don't know if it will. I'm probably not going to be around long enough to see it happen if it would. So, let's go ahead and keep looking at some stuff. Talk about some of these circular orbits. Right? You might remember we talked about circular orbits before. We did a really poor job of explaining them too, because when we said circular orbits last time, you might remember an equation that looks kind of like this. The velocity of our circular orbit is equal to the square root of r times g. And we said, okay, you can only do this on a perfectly spherical Earth where there is no air resistance and you're moving at a constant speed and nothing's going to get in your way, and only at the very surface of Earth, nowhere above that. And we didn't really focus on this because that's worthless, right? The Earth has an atmosphere. There's going to be air resistance. The Earth is not a perfect sphere. That's not going to work either. So I really didn't even bother with this equation too much because realistically, beyond that, it was kind of worthless for us. We did talk about what happens when we have a slightly different g, and then maybe it's a little bit more useful, but really this was a pretty incomplete picture. Now we have the tools to more accurately describe this. See, remember how we solved out g was essentially saying g is equal to g m over r squared. So if we plug that in, we multiply the r away, then we get some quantity like this, gm over r. Take the square root of that, and you have the velocity to go in a circle around any planet, regardless of the mass, regardless of how far away you are. Because largely speaking here, when you're just in the vastness of the universe, gravity is the only force you actually feel. So if I've got two planets, the only force between the two of them is going to be gravity. Not much else acting on them or anything else like that, so if they're just spinning around in one way or the other, gravity is going to be providing that centripetal force. So of course, when we solve out for it, this is the velocity that we would get to be moving in a perfect circle. But this was a little bit more useful because this can be used in a lot of different ways. We could talk about this with the moon, we could talk about it with satellites, all sorts of things like that. This would apply pretty well to those right there. Similarly, talking about more things about orbital motion. Orbital motion, you might have seen something in the text. It started a lot with Kepler's laws and the sort of nonsense that he went through in calculating a lot of these things. He didn't even have calculus to do this, and I can't even imagine what that would be like. To try and go through many of these equations without calculus or anything like that, it sounds insane to me. I mean, it literally took him years to go through, so understandably, right? But it kind of looks nasty. But anyways, we're not going to bother with the method of everything. Why bother with that when we've already got the answer right in front of us? So what we've got with all of this is essentially if we know that the planets are moving around at an average radius r, we can find the period of their orbit with this equation right here, Newton's form of Kepler's third law, or just call it Kepler's third. This tells us the period, capital T, based on essentially only the radius. If we know it's moving in a pretty constant orbit, then all you need is that average radius. And you're off to go. You're all set. Or rather, semi-major axis is what we should be saying for that one. But that's an equation that you can use occasionally, not as important as some of the others, but it is there in case we need it. And I've got a problem for you here. Here comes rotational motion with a steel chair again, right? I love that joke. It is one of my favorite memes. The equation, t squared over 4 pi squared. We've got this thing, of course, if you ever want to keep up with the slides and everything else, for one, it should be on the equation sheet. For two, you're always more than welcome to download the slides as well, just to make it a little bit easier to follow along with what I've got going on here. So here's what I'm thinking. We have this uneven kind of shape. This is a binary star system. And these are real things that exist in the universe. This is not just like a one-off kind of thing that sci-fi makes up with. You can have binary star systems. Here's what's going on, though. Each of these stars is orbiting around their common center of mass. So each star has its own mass, has its own distance r away from that center of mass. And I'm not going to ask you to calculate that center of mass. I'm just going to give you the values r1 and r2. So just work with those. No need to worry about too much of the stuff going on here. But what I will tell you is that both of these are going around in perfect circles. Not the same circles, because they've got different radii, but perfect circles, each of them. Knowing that they're going around in perfect circles, what is the orbital speed of each star, M1 and M2? So that is to say, find V1, find V2 in terms of these 4 variables. I'm going to say just take the next 4 or 5 minutes to work on this one, and then we're going to take a look together. All right, so let's take a look at this one. Here's what I'm thinking. I want to take a screen grab of this real fast, just so that in case we need it. Oh, we've already got it. Perfect. Slap it over in here. And we'll do it right there. Okay. So let's think about all the variables that we've got. We are asked to find V1, V2. We are given M1, M2, R1, R2. And the picture has been nice enough to do what I would have done anyways. They just called this distance right here D. I would have said the exact same thing. Hey, wouldn't it be really nice if we just had that variable? That'd make our lives a little bit easier. Sure. But they've given it to us in this case. We can't use it because it's not one of our givens, but it will help in getting all of our equations set up. So for each of these things, again, we are in the vastness of the universe. Stars are pretty big. In a binary system, they're usually pretty close like this. And that means that for the most part, no other forces are going to be acting on these things. The force of gravity between the two of them is going to be really the only force that matters. So what does that look like? Of course, gravity is always attractive. So I would say this force right here, F of G, is the exact same as this force right here, F of G. Now, each of these stuck in a circle. That means that each of them needs a centripetal force. How much centripetal force they need does depend on each star, though. It is not the same, well, it is kind of the same centripetal force, but let's talk about that. Let's label these slightly differently. I'll call this FC1, and I'll call this FC2. We'll talk about that in just a second here. Let's write that down. Each star needs to be staying in this perfect circle, a uniform circle, and that means that they must each experience a centripetal force. So FC1, star 1 over here, that's going to be M1 V1 squared divided by, well, R1. What's providing that centripetal force? The only force acting on the star, gravity. How much force is gravity providing? Well, we've got a handy equation for that. G, M1, M2, over the distance between the center of their masses, D. Now, I'm going to take that one step further, right? And I'm going to go ahead and say, hey, D is not one of my given variables, but looking at my picture here, D is just R1 plus R2. So this, G, M1, M2, divided by R1 plus R2. Squared. Now, I'm looking for V1. I see it right in this equation right here, so I'm going to combine these two. I'm going to say, all right, well, this is going to become divide each side by M1. That is, V1 squared divided by R1 is equal to G M2 divided by R1 plus R2. Take a square root, or first multiply by R1, then take a square root. V1 is equal to the square root G M2 R1 divided by R1 plus R2 squared. And that, a little bit misplaced there, is the velocity that it takes to stay in that circle. Now, we can do the exact same thing with V2, and actually, I'm not even going to write a new equation. I'm just going to take the one that I've already got up top here. Because The centripetal force that 2 needs is also coming from gravity. It's not coming from anywhere else, so it too is going to be m2 v2 squared divided by r2. No different. And we can go through the exact same solving process, and the fact of the matter is that the 1s and the 2s switch places. That's the real difference between the two of them here. This is going to become v2 is equal to g m1 r2 divided by r1 plus r2 squared. Take a square root of the entire thing. And that's what we end up with. Can you guys imagine what we would have done if we would have seen this in like week 1 or week 2? When we first started talking about gravity and free fall acceleration, could you imagine what we would have, the drop rate for the course, what that would have been with all of this stuff? It would not have been super pretty. But at this point, you've mastered a lot of that stuff, right? Think about how far you've come with a lot of these things, that this equation's like, oh, this is one of the nicer ones, right? You guys have come pretty far here. Quite the journey indeed, and it's not over yet. We still have another few weeks here. Still get to keep having some fun for a while. But I'm not seeing any questions, so let's go ahead. I've got one last slide that I do want to talk about here, because realistically, circles are not a very common shape in the universe, but ellipses are. So a lot of the time, what we can do, this is just kind of one last little detail that I've got here for today, that if you're looking at a realistic orbit, like most planets are not perfectly circular, they actually go in these ellipses shapes, we run into a little bit of an issue because, technically speaking, being an ellipse, it means that the force felt by the planet orbiting the star is not constant. Yikes. Kinematics doesn't like a non-constant force. However, energy conservation really doesn't care that much. So this is just kind of pointing out the fact that if you know the details about any one point of an orbit, if I knew the speed and the distance away of this spot in the orbit, then I could figure out what the speed and distance away are at any other spot in the orbit, knowing that energy must be conserved because gravity is a conservative force. That means that I could take any 2 points in the orbit and relate them with an energy conservation equation. So I just want to bring that up because you can use that. There might be a problem or two where you use this idea that energy is conserved all the way throughout the entire orbit. If energy wasn't conserved, then we would have fallen into the sun a very long time ago. But the fact that we're still rotating around here, haven't crashed into the sun quite yet, I would gander that energy conservation probably works pretty well. So that's all I've got for right now. I'm going to send out an announcement about that orbital motion lab in just a little bit here. I have uploaded a couple of the programs so far, but I want to check to make sure that everything works all together. Again, that will be an optional assignment though, because you're going to have to download a program and trust that the program is going to work. And you're probably going to have to tell your operating system, yes, I want to run this. I know it can have viruses and all that stuff like that. I'm fairly positive it doesn't have viruses. I have run it on my own computer, but it's optional. It's an open source kind of deal, so I would expect that if it had issues so far, they would have lost funding, and they are still funded by coolmathgames.com and Newgrounds and a lot of those other places, so I would expect that by now they probably would have been shut down otherwise, because Cool Math Games has never broken my heart before, and I don't expect them to anytime soon. The Dark Matter Lab just uses Excel. There is no simulation part about that. You are just essentially realizing what the numbers would look like. Sure, yeah, it's up right now. You should have all the information you need for that one. I will talk about it in a little bit more detail next time around, but you should have most of the tools, and if not, the slides are up that you can look at them to get a little bit more context as to what's going on with those, if you're interested in any of that stuff. But that's all I got for the day. Thanks for being here, team. I always appreciate it, of course. And I will see everyone again next time.